All right, today we're in section 5.4, special systems of linear equations. This is our last lesson on systems of linear equations, and by special we mean that we're going to have solutions that are outside of what we are used to seeing. Okay, so that's what this slide's talking about, that we could have one solution, and that's what we've been looking at for sections 1, 2, and 3. We've been looking at systems of equations that have one solution, and it's an ordered pair. All right, well, today we're going to look at systems that have no solution and systems that have infinite solutions. Okay, so for no solution is on a graph, it looks like parallel lines, because you've got to think about it. If it's a solution, the lines are going to intersect, and where they intersect is your solution. So if it's no solution, that means that those lines never intersect. And we know that there are some markers for identifying parallel lines, right? Parallel lines have the same what? Parallel lines have the same slope. Same slope. That will help you on number 19 on your homework tonight. Parallel lines have the same slope. Okay? Infinite solution means that it's the same line. If I were to graph it, it's the exact same line. And then there's also ways that I can identify that not on a graph. So we're going to look at just our different options. Okay? Next slide. So in this section, all right, so on your quiz, basically, let me kind of give you an outline of what your quiz and tests are going to look like. You're going to have a graphing section, a substitution section, and an elimination section. And then you're going to have a section for special equations. And in this section, you're not going to be told which method to use. You're going to have to figure out, do I graph, substitute, or eliminate to come up with my solution? Now, in the special systems section, there might still be an answer, an ordered pair that's an answer, but there could also be a no solution or an infinite solution answer. So we need to know, how do I look at a system and know, am I supposed to graph this? Am I supposed to substitute or eliminate, or do I have a couple different options? Well, we've kind of written down here some helpful tips to know when you do which method. All right, so go ahead and write that down. We'll talk about it more in just a second. So let's go through each one of these. So for graphing, you're looking for a system that's already written in slope-intercept form. So if it's in slope-intercept, it's not difficult to graph, especially at this point, because we've already been tested over this, to graph a linear equation. That's not difficult. And then we just see where they cross and we're good. However, it's not necessarily the ideal method. And how many systems do we really have that are both already in slope-intercept? Very few. Okay, so substitution and elimination are really where the majority of our problems are going to be solved with one of these two methods. So how do I know when I use one or when I use the other? With substitution, I'm looking for a simple equation where x or y is already solved for, or easy, maybe like one little step to get x or y by itself. With elimination, I'm looking for x or y to be easily canceled out. So opposites. And that's the method that we learned yesterday. All right, so see, here are some sample systems that would really fall in line with each method. So for graphing, what do you notice about each equation on the graphing? They're ready to graph. Both equations are ready to graph. I just plot the points on the lines and I'm done. And especially if the graph is already like right there next to me, that's going to be pretty simple. All right, so graphing to solve. And then let's look at the second ones. All right, I want to give you a minute to write them down. Hopefully it won't take too long. All right. Hint, write fast. All right, so go ahead and write down the other two systems. Okay, so now let's look at this second system, substitution. What in this system, so if I didn't have substitution as the title, what in here is a clue as to, hey, substitution would be a pretty easy method to use here? What's your clue here? We said what? That one of the variables needs to be solved for, right? So because x is by itself, I know that 2y plus 2 can be plugged in for x if I were to solve this. So I'm looking for one of the variables to be solved for, and I can substitute that value into the other equation. All right, now elimination, I'm looking for what? What in this system tells me that elimination is probably going to be the method that I want to pick? What is it in here that tells me elimination is probably the method I want? Haley? Yes, 4y and negative 4y, they cancel out. So elimination allows me to cancel out those terms and solve for x. All right, so you have to know what those markers or indicators are to help you figure out which method you're going to choose. All right, because again, this section on the quiz, it's not going to tell you what method to choose. You're going to have to know what method. All right, so let's look at the first equation, system. All right, y equals 3x plus 1 and y equals 3x minus 3. All right, so if you, I would say, kind of tend to enjoy graphing, this would be a pretty ideal system to graph, wouldn't it? Right? What indicates to me that this is a good one to graph? Sardian slope intercept. Both equations are ready to graph. However, graphing usually is not our first choice for a method if we have other options, and we do here. All right, so y equals, when the variable is isolated on one side of the equation, when the variable is solved for, what method says I could easily solve using this method? Elimination. Not elimination, but substitution. Because if y equals 3x plus 1, I can plug it in the other equation for y. Okay, so substitution says if one of the variables is solved for, I can plug in what it's equal to into the other equation for that variable. So that's what we're going to do. We're going to do substitution. All right, now I could have used elimination also, but I would have had to multiply the whole equation, and that's just a little more work. So I kind of want to steer you more towards the substitution. All right, so we have 3x plus 1 equals 3x minus 3. Does everybody see how I got that? I took the y equals part and I plugged it in the second one for y. 3x plus 1 equals 3x minus 3. All right, made them equal to each other. And we actually solved some of these already. All right, in our substitution lesson, we solved these where we had variables on both sides of the equation. What did we have to do? Does anybody remember? Yeah, we need the variables on one side of the equation and our numbers on the other side. All right, so how could I move 3x to the other side? Subtract 3x. All right, I'm just following the normal process that I usually follow. All right, so what happens? Cancels out. And then when I subtract the other side, what happens? Oh my goodness, it cancels out too. Okay, so because they both cancel, this is where we start seeing something different happen. They should not be both canceling. But when they do, and the x terms are gone, all I have left is 1 equals negative 3. It's all I have left. Is that true? Does 1 equal negative 3? No. No solution. All right, so if you're trying to solve and then all of a sudden your variables cancel out, that's not supposed to happen. So now your radar is going up and you're thinking, okay, this is going to be probably no solution or infinite solution. I need to see now if the remaining values equal each other. All right, go ahead and write down your second system. Go ahead and write down the second system. Y equals negative 5x minus 2 and 5x plus y equals 0. As you're writing it down, I want you to think, should I do graphing, elimination, or substitution? All right, don't say it out loud. Write down the system and think, what method would you choose? Got it written down? All right, so do you want to do graphing on this? Are they in slope-intercept form ready to graph? No, and it would take some work, and then I have to set up my graph, and I really don't want to do that if I have another option. All right, and if I need to do elimination, that means I have to line up all my terms. So I have to move my terms around on the equation. That's going to take work. So what do you think makes substitution kind of the obvious pick, other than just eliminating the other two options? What in this equation says, yeah, substitution is pretty doable? Y is solved for. Guys, do you get that? Do you see that? Y is solved for right here. That should make your radar go off that substitution is the one to pick. Okay? So y equals negative 5x minus 2. What do you do with that? What do you do with that? Plug it in for y in the other equation. All right? This is something that, we've learned. Okay? We just need to keep sharpening those skills. All right? So go ahead and plug it in. Y equals negative 5x minus 2, so plug that in for y on the other equation. All right, so plug them in. 5x plus negative 5x minus 2 equals 0. Now this plus and negative, okay, so I've seen that kind of written on, maybe some of you even wrote that on your paper, because there was already a plus sign here. And then I plugged in a negative 5x, but plus and negative is the same thing as what? Just subtracting it. So don't write plus and negative, just write a minus, okay? We want to get away from those double signs. Plus and negative is the same thing as minus. So what is 5x minus 5x? 0. Cancels out. Okay? They cancel. So what am I left with?
Negative 2 equals 0.
No solution. All right? Did you maybe get that before we put it up there? Okay? So with no solution, my variables cancel out completely. All right? And that's how I know it's no solution. All right, let's look at the next slide. X plus 2y equals 6. And 3x plus 6y equals 18. Let's go ahead and set up that system. Okay, so you guys want a graph to solve this? Is that an ideal system to graph? No, it's not even close. All right, now substitution. Now I've had a couple students today, they're like, I just love substitution. If I can make it work, then I want to do substitution. Well, could you move this, the first one around just a little bit to do substitution? Subtract 2y to the other side. X equals 6 minus 2y, and then you could substitute it for x. You absolutely could do that. However, don't write that down. We're not going to substitute. You could, but the clear choice, in my opinion, is elimination. Okay? We're looking for a clear connection between our x's or our y's. What could I multiply my x term by to get my x's to cancel? Or what could I multiply my y term by to get my y's to cancel? Okay? What do you think? So the top equation, I can multiply, what would I have to multiply x by to get that term to cancel with 3x? Negative 3. Negative 3. It's got to be negative because I need it to be negative 3x in order to cancel out with the positive 3x. But don't stop here. So again, I'm struggling with this part of it with you guys. Y'all are just stopping and then you're writing the rest of your equation and you're forgetting to distribute the negative 3 through the rest of the equation. You have to keep multiplying it. What's negative 3 times 2y? Negative 6y. What's negative 3 times 6? Negative 18. And then I have 3x plus 6y equals 18. All right? So now, mission accomplished. I need my x's to cancel. That's great. And in the past, that's what I needed to do. Get my x's to cancel, and now I can solve for y. However, this is where I start running into kind of something different. What happens when I try to simplify my y? It cancels out also. What happens when I try to do negative 18 plus 18? It cancels out too. So 0 equals 0. They both cancel. But is it still true that 0 equals 0? So my answer is infinite solution. Now, if it was 0 equaled any other value, it would be no solution. But because both sides actually do equal each other, then my answer is infinite solution. Meaning that I could plug in whatever XY combination I wanted into this system and it would make both equations true. All right, so now let's look at the last one. Go ahead and write down your last system. 2x plus y equals 5 and 4x plus 2y equals 0. Okay, so what do you think? Substitution, elimination? Substitution, so maybe you could say subtract 2x to the right side and y equals 5 minus 2x if you wanted to do substitution. Okay, I would choose elimination. All right, just because I just tend to favor elimination. That's the method that I like to use. All right, so again, I have to figure out how can I get my x's or my y's to cancel, either one. And then I multiply the whole equation by that value. I just like to do x because it's the first variable, if there's a connection. So from 2 to 4, is there something I can multiply the first 2 by to get it to be the opposite of 4x? Don't say it out loud. Go ahead and write it down in your notes. What could I multiply that top equation by that would make my x term the opposite of the other x term? Go ahead and write down that number outside the parentheses. I think Haley knows. Does anybody else know? Desiree? What is it? Negative 2. Very good. It's going to be negative 2 because now negative 2 times 2x is negative 4x, and I needed it to be the opposite of positive 4x. But I'm not done yet. I need to keep distributing the negative 2 to create an equivalent equation. What's negative 2 times 1y?
Negative 2.
Negative 2y. What's negative 2 times 5? Negative 10. All right, now I'm going to rewrite the other equation underneath. All right, and now I can start solving. I can start adding them together. What's negative 4x plus 4x? Cancels. That's what I wanted. What's negative 2y plus 2y? Cancels again. Wasn't necessarily planning on that happening, so if everything cancels, it's just 0. All right, well that's okay because as long as the other side is 0, then it's infinite solution. What's negative 10 minus 0? Negative 10. No solution. Those values are not equal. All right. Now again, guys, this only happens when my variables cancel out. They're not supposed to cancel out. This is something different or unique about linear systems. Most of your linear systems will have a solution, an ordered pair, an x value and a y value. Follow me on that?
Yes, ma'am.
Okay. All right, so that's everything you need to know for 5.4, and all of chapter 5 is done now. All right, so we're going to spend, the rest of, our time between now and the test just reviewing these concepts and practicing them more.